So you remember what we're doing? We're doing volume by slices. Volume by slices. And usually we will have two types of a picture. We'll either slice x-axis, so slice perpendicular to x-axis, so two cases. So we're going to slice perpendicular to x-axis. So that kind of mean we're going to have a picture which looks something like that. Then we have our object. Okay. And then our slices look something like this, right? Okay. And in this case, we're going to get volume equals integral x equals to a, x equals to b. So that's where we start slicing, and that's where we finish slicing. Dx, a of x, where that a of x is the area of cross section. Okay. So dx becomes with dx because we're slicing x-axis, and we're going to see those like delta x here. Okay. So that's the reason. And dx insists that everything should be in terms of x. And if we slice perpendicular to y-axis, then our picture going to look similar, but basically what we'll do, we'll just exchange, instead of x, we're going to have y. Otherwise, it's going to be kind of similar. So starts at C, we finish at D, then we have curve, right? And not the curve, but I guess object, solid, three-dimensional. Then we start slicing. We start slicing. So when we slicing, we have those traces on y-axis, and our slices are going to look something like this. So we're going to have horizontal slices. When we slice in y-axis, we're going to put vertical slices, and we're going to slice x-axis. So volume in this case, again, you see that's going to be similar to what we get. The only thing is going to be changed, and instead of x, we're going to have y. So that's the difference. And again, a y will be the area of cross section. So that's an idea. Say we have a sphere, right? So we have a sphere, and then from a sphere, we cut kind of a little bit from the top. So let's imagine the following picture. So we have a sphere, right? And we have some radius on it. And then from the sphere, we cut that, that part from the top, okay? Cut that top, okay? And we will wonder what will be the volume. Okay. So let's introduce some numbers, and then maybe we'll be able to do the calculations. So first thing we need to know the volume of the area, radius of the sphere. Okay, so I guess I will need a number. 4. Let's pick 4. Radius 4. Now, from that sphere of radius 4, again, we cut that top part. And the top part, let's see how it's going to be located. So when we cut it off, somewhere here, right? Perpendicular to the radius, that's how our cut is going to happen. So what's this number? Should be less than 4, right? So it may be 1, 2, 3. According to my picture, it's probably 3. Maybe 3.5, but I kind of want to work with whole numbers, so let's put like 3 here. Works for you? Okay. So now the question is, what is the volume? Of that cut of piece. Okay. So I provided a lot of verbal description of the problem, and so I hope that's clear what I mean. I didn't write it because writing might take a little bit more time than I want. So I guess I will redraw a picture. Okay. And 3 somewhere here, 4 somewhere here. So we have a trace, image, shadow of a sphere on XY plane. Okay. And we're interested in finding that piece, right? Basically. Now just imagine that when we will be starting and doing the cuts, our cuts, if the shades are going to be here. Right? Just imagine, it's again, it's projection on XY plane. So those are what is traces on XY plane. So volume is going to be equal integral. We know we start at 3. We start cuts at 3. We finish cuts at 4. Y equals to 4. Y equals to 3. We know it's dy because we cut in y-axis. The only thing which is left to figure out what will be area of cross section. So let's look at the cross section. Let's visualize the cross section. Try to use blue. So you see the cross section, it's kind of popping up if I try to pop it up and make it 3-dimensional. So cross section is going to be circle. Circle. So area is going to be pi r squared. Okay. And now again, if you look at this picture for cross section, do you see that's radius of cross section? So it's r. And if I pick, if I look what is going on, that is horizontal. And horizontal means x coordinate of a point. Okay, so that is, if I pick that point has coordinates x and y, then in terms of x and y, that will be x coordinate of a point. R equals to x. So that equals to pi x squared. Volume equals y equals to 3, y equals to 4, pi x squared dy. Then we can easily find out the derivative of x squared, which is x cubed over 3. We're doing it from y equals to 3 to y equals to 4. And then we realize we did a mistake, right? Because just imagine if I start trying to write down pi x cubed over 3, y equals to 3, y equals to 4. I know that I did a mistake because I should finish my kind of substitution, right? So just be careful, that part dy is important. Okay, so don't jump to that conclusion that an antiderivative of x squared is x cubed over 3, because we have to integrate with respect to y. So we yet to finish our substitution. So to finish the substitution, we look at the circle. Circle has equation x squared plus y squared equals to 16. So from here, x squared equals to 16 minus y squared, and that's what we're going to be substituting for x squared. So we're going to get integral y equals to 3, y equals to 4, limits, pi 16 minus y squared dy. And now we can integrate. Pi is a constant, I'm going to take it outside. Antiderivative of 16 is 16y. Antiderivative of y squared y cubed over 3. We're doing it from 3 to 4. So we're going to get pi 16 times 4 minus 4 cubed over 3 minus 16 times 3 minus 3 cubed over 3. Pi 16 times 4 is 64. 64 minus 4 cubed over 8. Let's see. 128 over 3, if I'm correct. Minus 16 times 3 is 48. 3 cubed over 3 is 9. And pi 128 over 3. 48 minus 9 is 39. Minus 39. So we're going to get pi 3, 128 minus 33 times 3. Pi 3. I want to say 11 pi over 3, but I might have done a mistake because I basically, when you get here, just doesn't work to do a calculation by hand. Just grab a calculator or something like that. So at least I get 11 pi over 3. I might have done a mistake. So. Let's do problems where we will be working with objects of revolution when we're going to rotate region, and the situation when we might have holes inside. So let's do firstly without hole, and then do problem with a hole. So, the region R is bounded by, say, y equals to square root of x, x-axis, and x equals to 4. Okay, so what's the region? Now, the region R is rotated around x-axis. Find the volume. Of the solid. Find the volume of this solid, which we're going to obtain. Square root of x, x equals to 4, x-axis. Okay, so what's the region R? Okay. Now what we do with it, we're going to rotate it around x-axis. We're rotating around x-axis. So we rotate in the region. So if I rotate, I'm going to see its symmetrical image on the overside when we rotating. So on the overside of x-axis. And then to visualize, to help me to visualize, to see three-dimensional object, I probably will connect opposite endpoints by something like kind of your three-dimensional perpendicular circles. So hopefully you see the object which we're talking about. That's the object we're talking about. Okay. So I'll try to draw as many pictures as possible before I got like solid understanding of what's going on. Now I want to see my slices. I want to see my slices. So I'm going to slice x-axis. So we're going to have vertical slices. Slices are going to look something like this. Okay, I see circular slices. So this is going to help me figure out the area of cross section. Okay, so I try to write down our volume. So volume equals integral. I start integration at 0 and finish it here, and here a point was 4, right? X equals to 4. 0 to 4. And I will have area of cross section, dx. I know cross section is going to be circular. So pi r squared dx. So all that is left is figure out what is r. So let's have a look. R. R is this guy. R. This point has coordinates x and y. Because r is vertical distance toward the point from x-axis, vertical distance toward the point is y coordinate. So we're going to get integral x equals to 0, x equals to 4 pi y squared x. Okay. Now x and y comes from that curve. That curve has equation y equals to root of x. So we take y equals root of x, and we're going to substitute it for y here. So we're going to get integral x equals to 0, x equals to 4 pi square root of x squared dx. Take pi out, 0, 4 x dx pi x squared over 2 from 0 to 4, 8 pi the region R is bounded by y equals to x squared, y equals to x, y equals to x. So the region R is rotated around x-axis find the volume of the solid, or the solid of rotation when R is rotated around X. Okay. There are a couple of ways how we can address the situation. Okay. I guess first level it should introduce the washer. We can do it with washer. So let's see. What is a washer? A washer is thin three-dimensional object, which basically you're thin, and it has a hole inside. It's very thin. Okay. It's solid, but it's very thin. So it has some thickness, right? Thickness. We kind of say it's H, just look sideways, right? And then it has inside radius and outside radius. Outside radius R, big one, and also we'll have that small radius and inner radius. Little r. Okay. That's a washer. Then volume of a washer equals. So you basically will do the following. To find the washer, we'll do that. So we calculate the volume of the whole thing, and then we subtract the whole. So pi r squared h minus pi little r squared h. That's the first comment. And second, also area of cross section in this case is going to be pi r squared minus pi r squared, pi capital R squared minus pi little. Right, same reason, because we're doing big minus small minus whole. We're doing washer because often we're going to see if we have a hole inside of our three-dimensional solid, then it's going to be a washer as a cross section. So either this one or that one, some of these formulas might be useful. Okay. So now let's go back to a problem. So let's go back to the problem. So we have y equals to x, y equals to square root of y equals to x squared. So that's the region R. And if you look, the intersection point is going to be 1, 1. So that's the region R. And now we're rotating that region around x-axis. So if you're rotating it, when they're going to draw a copy on the overside, And then we are going to connect opposite edges, this one and that one, to get an idea how object is going to look like. But also for this object, we're going to see inside of it is going to be whole. So our object, I'll draw it inside one more time. Looks like this. And inside of object, we have that whole. So hopefully you can see it. Anyhow, volume equals to integral dx, because we're going to cross cut x-axis. X starts here, x ends there. We're going to start at x equals to 0, and we will finish at x equals to 1. And here, area of cross section. Let's visualize the cross section. So visualize the cross section. So hopefully we see a washer. So cross section is a washer. Washer. So area is going to be pi capital R squared minus pi little r squared. So it's area. Now let's work with it a bit more. So that's the region. Now let's visualize where we have washer here. Okay, so washer right here. Okay, so what's our washer? And you see that washer kind of have 2 points of intersection with our region, right? 2 points. So we have 2 points of intersection. Because we are on vertical segment, we're going to have the same y, but 2 different y's. I'm going to call it y top, y bottom. Okay. Now, if I look at this picture, I see that outer radius is going to be from here to here. And you see outer radius is measured from top point toward x-axis. So it's y top. Inner radius is going to be this piece. So it's this piece. And you see it's the distance toward the bottom point from x-axis, so it's y bottom. And as soon as we realize that, we are ready to write down y top squared minus pi y. Okay, so we get volume equals integral x equals to 0, x equals to 1. Pi y top squared minus pi y bottom squared dx. Let's have a look again at our curve, our region. So y top comes from here, y bottom comes from there. So y top comes from a top curve, y bottom comes from the bottom curve. Top curve has equation y equals to x. So actually y top equals to x. Bottom equation has equation y equals to x squared. So y bottom equals to x. So we take y top equals to x. We substitute with y top, y bottom equals to x squared. We substitute in for y bottom. Because don't forget, we need to have integral in terms of y, not in terms of y, in terms of x. So we're going to get integral x equals 0, x equals 1, pi. Y top is x squared minus pi. So our y bottom is x squared, so x squared squared. And that is reasonably easy enough integral to calculate. Pi x cubed over minus pi x to 5 over 5 from 0 to 1. So pi over 3 minus pi